Okay, we are continuing from last time. Yaakov is here. Say hi. Does it see you? Yeah, it does. Very nice. All right, we are continuing the theorem from last time, which is the third part of the theorem. Let's just rewrite the theorem. So the theorem says the following are equivalent. So what is that? So first, that f has an antiderivative. We call it capital F of z. Second, that the integral along a curve gamma of f dz is capital F of zf minus capital F of z naught. And lastly, that the closed integral over any curve dz equals 0. These are equivalent statements. Let's call it 1, 2, and 3. 1, 2, and 3. And recall, last time we showed that 1 implies 2, and that 2 implies 3. Now we want to show that 3 implies 1. Right, that 3 implies 1, and that would make them all equivalent because there is a cycle of implication. All right, so let's do the proof. All right, so 3 implies 1. That means that we have a function f which satisfies that any closed integral gamma of that f dz is 0. And we could say, d gamma subset of some d subset of c. Well, what does this tell us? Well, from this we could define a capital F of z, which is we will have to demonstrate that this capital F of z is the antiderivative of lowercase f, but we don't have that for granted. What we could do is we could make a definition for it. It will be the integral over gamma of f dz, where gamma of 0 is equal to some z naught. We call that x naught comma y naught. And gamma of tf equal z equal x comma y. And the idea is to demonstrate, we need to show that f prime z is this lowercase f. So first of all, note f is well defined, since its value is independent of the curve gamma by assumption, because if there was let's do a quick proof. Say we had gamma 1, gamma 2, each satisfying gamma 1 of 0 equals gamma 2 of 0 equals z naught, and gamma 1 of tf equals gamma 2 of tf equal z. Then, by assumption, the integral the closed integral made by gamma 1 after gamma 2 of f dz is by hypothesis 0, right, which tells you thus the integral under gamma 1 of f dz equals the integral of gamma 2 of f dz, and so f is well defined and independent of path. Okay, so it's a good definition. Now we need to demonstrate that the derivative, the complex derivative, returns the initial function f. So, well, let's do an analysis. First, let's consider, we will name this point z0. So this over here is z0, and it could be labeled as x0, comma y0. Let me put the labeling a little bit lower. So z0 equals x0, comma y0. Let this be the point z. Z equals x, comma y. And let this be our curve gamma. Now, since gamma is changing both in the x direction and the y direction, it's a little bit unclear what the derivative with respect to time is, or the derivative with respect to z. So what we can do, using the fact that it's independent of path, we could create two new paths. The first one goes all the way from here until this coordinate is x, comma y0, and then from there it goes all the way up to here. That's the first curve. And the second curve will do a similar action, but along the vertical direction. So this coordinate is x naught y, as opposed to x, y naught. We could name these. This will be gamma 1, this will be gamma 2, this will be gamma 3, this will be gamma 4. By assumption, the integral along gamma of f dz is equal to the integral along gamma 1 of f dz plus the integral along gamma 2 of f dz, and this as well is equal to the integral along gamma 3 of f dz plus the integral along gamma 4 of f dz. Okay, now what are all these? The integral, well, let's just rewrite the equivalence. So this is the integral along gamma 1 of u plus iv times dx plus I dy plus the integral along gamma 2 of u plus iv times dx plus I dy, and this is equal to the integral along gamma 3 of u plus iv dx plus I dy plus the integral along gamma 4 of u plus iv dx plus I dy. Okay, we could expand these. So this, I will expand the first equation, is the integral along gamma 1 of u dx minus v dy plus I u dy plus v dx. Okay, plus, we will first pay attention to the first equation and then we'll deal with the second one, plus the integral along gamma 2 of u dx minus v dy plus I u dy minus v dx. Okay, now notice that under our definitions for gamma 1 and gamma 2, along gamma 1, the dx element is 0, because there's no differential with respect to x. It's only moving in the y-coordinate. And so over here, u dx is 0, minus v dy is non-zero, and the v dx over here is 0. Similarly, along gamma 2, there's no movement in the y direction, and so the v dy is 0, and the u and the u dy over here is 0 as well. And so what we get finally is the integral along gamma 1 of minus v dy plus I times u dy. And then, of course, plus the integral along gamma 2 of u dx plus I, well, really minus I e dx. Each of these individually are integrals with respect to a single variable. And so what we can do is we could separate it out and turn it into real valued integrals. So we'll do that over here. I don't know how much of this is actually on the screen. Yeah. All right, perfect. Okay. Now, all right. So what do we have? We can rewrite. This. So this is the integral along gamma 1 of minus v plus iu minus v plus, well, let's say it this way, minus v dy plus I along gamma 1 of u dy. Again, gamma 1 has changes with respect to y, plus the integral along gamma 2 of u dx plus I times the integral along gamma 2 of v dx, of minus v dx. Okay? Now recall, right, df dz equals f sub x minus I f sub y over 2 plus f sub x plus I f sub y over 2 dz bar dz, where z bar is the complex conjugate. Now, in terms of the derivative with respect to x over here, if this over here, this whole thing is capital F, this is capital F of z, we may take the derivative with respect to x. I'm sorry, these should be uppercase, 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 uppercase. F z, the derivative with respect to x equals, well, so the derivative with respect to x of this thing, this has no x's, so it goes away. What we're left with is this. These are ordinary real valued derivatives. Gamma 2 starts from here and ends at here. And so this is the partial with respect to x of the integral from x naught to x of u dx hat plus the integral from x naught to x of I v, well, minus v dx hat. These are real valued integrals, so we can apply the fundamental theorem, and we get that this is nothing but u of x comma y plus, or really minus I v of x comma y. All right, that's the partial with respect to x. Now we need to find the partial of f with respect to y. And what we're going to do is we're going to do the same analysis, but along the curves gamma 3 and gamma 4. So let's do that. Okay. We can rewrite f using the second equation. And so what we have is that f of z is equal to the integral along gamma 3. Well, gamma 3 doesn't have, is not moving in the y direction, so all of the dy components are 0. this over here is 0, and this over here is 0, leaving us with a u dx plus iv dx. U dx plus gamma 3, put the I on the outside, iv dx. So that's along the gamma 3. Gamma 4 doesn't change in the x direction, it changes only in the y direction. And so over here, when we have gamma 4, u plus iv dx plus I dy, the dx element is 0, and we just get an I dy. And so this is plus the integral along gamma 4, right? Integral along gamma 4 of u I dy minus v dy. U, let's put the I on the outside, u I dy minus the integral along gamma 4 of v dy. Right? Okay, now we can consider the partial with respect to y. So the first terms, the gamma 3 terms, are 0 with respect to y, and what we're left with is this. So this is the partial with respect to y of I y naught y u dy bar, or dy hat, plus d dy times negative integral y naught y v dy hat. We can apply the fundamental theorem of calculus, and this gives us u of x comma y, rather I times ux comma y, and then we have minus v of x comma y. All right, so now we can consider the full complex derivative, f of z, we can say df dz. It's an ordinary derivative. And what is this? Well, we know already that this is, using these equations, we can plug in the values of f sub x and f sub y. So, we'll do that. So, it's f sub x minus I f sub y. F sub x is u plus u minus iv, and f sub y is v, iu minus v. So, u minus iv plus, not plus, minus I times iu minus v. And this over 2 plus, and this term better be 0 because it's the coefficient of dz bar over dz, which must be 0. And so what do we write? It's f sub x plus I f sub y over 2. So f sub x again, u minus iv plus I times iu minus v over 2. Delta z r delta z. It's clear that u plus I times u is 0. So these cancel. Minus iv plus I times negative v is of course 0 as well. So this part is 0. Okay, over here, so that's what we have left. We have a u, but then we have a minus iu. I times I is negative 1. Negative 1 is positive 1. So we get 2u. Now I have this iv minus iv, or rather, this is a negative. Negative times negative is positive. I times positive is iv. Over here I have minus, is it minus iv or plus iv? Minus iv, there's a minus sign, it's a plus what is the partial with respect to y? The partial with respect to y is iu minus v. Iu minus v. Minus v or plus v? I'm missing a plus sign. So here's plus, so here's minus I. 2u, I times I is negative 1. Positive u plus u. Good. This is positive v, positive iv. This is a negative iv. That's a negative iv. That's not good. U minus iv. U minus iv. Negative came from here. This came from here. Here. Minus iv. Okay. Fine. This is plus minus v dy. Let's see where that came from. Well, that came from here. I minus v dy, so I times I dy, that's the minus v dy. That's where that came from. What is going on with the minus sign? Plus iv. Minus iv plus iv. That should be a plus. This should be a plus probably. F sub x is this. So this is called question. Where did that come from? Minus v. That's from here. This we're doing all the x's. So that must have come from plus over here. Let's just be careful. We have u dx, all the dy terms are 0 along gamma 1. So it's u dx, v dy is gone. But over here I have iv dx. iv dx. This is positive. This is positive. I don't know why I put a negative there. Okay, this is positive. And therefore this is positive. And therefore this is positive. And therefore we have plus 2v over 2. And this is u plus 2iv, u plus iv. Okay, so that's the first method of proof. I would like to demonstrate another one. So, all right. Okay. Very good, very good. All right, second proof. Well, we take it for granted that the closed integral around any gamma of f dz is 0. By assumption. What does this mean? Well, we can infer from this that the closed integral around gamma of u plus iv dx plus I dy equals 0. This is the closed integral of u dx minus v dy plus I of u dy plus v dx. Alright, this is a real valued integral, this is a real valued closed integral. These are line integrals, more specifically. Though there's the I over here, it's on the outside, so it doesn't affect the inside. And we could use now Green's theorem, which says, alright, so recall, right? If let's say capital F of xy equals what's typical? Let's say p of x comma y plus q of x comma y. Then the integral of p dx plus q dy. This, by the way, is nothing but capital F dot dr. So this is just a real valued line integral, is equal to the double integral over the domain, well, d gamma, I guess, of the partial of q with respect to x minus the partial of p with respect to y, dx dy. And again, if it's an analytic function, of course, if I take right, if it's an analytic function, it is a gradient of a scalar field, which means that this, well, of course, these are times I times j. This is a gradient, which means that this is the partial with respect to x, this is the partial with respect to y. So, of course, if I now take the partial of this with respect to x, and I take the partial of this with respect to y, they should be the same, which would make this 0, which would make the line integral 0, and that's why the line integral of conservative vector fields are 0. But over here, we don't know that this is a result of a scalar field, and so we have to argue a separate argument. So we can apply, however, Green's theorem, but we don't know for sure that it's 0. So let's apply it. So, okay. So over here, you could write thus. We have, okay, that the integral along gamma of u dx minus v dy is equal to the double integral along d gamma of negative v sub x minus v sub x plus or minus u sub y minus u sub y dA. And of course we have this other term, this I term, plus I times double integral over d gamma of course these are closed. Let me rewrite this. D gamma of u of partial u with respect to x, or minus plus u sub x minus v sub y dx dy. Okay, now you'll notice that that if f was analytic, ux will equal vy, and so this will be 0. Further, uy will be minus vx. So if uy is minus vx minus uy is 0 as well. But that's assuming f is analytic, which we don't have for granted. But we do have this is 0. So by the fact that it's 0, it means that each of these individually are 0, because this is imaginary and this is not. Well, that tells us, so therefore, we have, right, that the double integral, again, write this again, d gamma of, well, the minus sign doesn't matter anymore, we can just get rid of it, because it equals 0 anyway, of u sub y plus v sub x dA equals 0. This is the first one, and the second one, the double integral d gamma of ux minus vy dA equals 0. Now the question is, can we infer that, well, firstly, u sub y. Can we infer that the integrand is 0? In other words, that u sub y plus v sub x is identically 0, and that u sub x minus v sub y is 0. It's unclear because this is integrating over a domain. It could be that part of the domain will give negative contribution and part of it will give positive contribution. Therefore, it's unclear whether the integrals being 0 implies that the integrands are 0 themselves. But the claim is that yes, this follows. And now we're going to have to prove this claim. So let's prove it. Proof. Well, if it wasn't, then there would be, so let z naught be a point in d gamma with u sub y plus v sub x non-equal to 0, and v sub x and u sub x minus v sub y not equal to 0. It follows that there exists a ball surrounding z naught of radius epsilon with uy plus vx not equal to 0 for all z in b z naught epsilon, and that ux minus vy equals not equal to 0, again for all z in b z naught epsilon. And this follows from the fact that u and v are differentiable. Okay, well, that means that now we can take gamma to be the boundary of b z naught epsilon. Well, actually, we can make it even stronger. Let z naught be a point in d gamma with not only that it's non-zero, but that it's positive. Such could be assumed because if it didn't exist, then we will just take one where it's negative instead. And if neither z naught exists for positive or negative, then we are back to where we started. And the proof is complete. Therefore, either there's a point in which it's positive or it's negative. The proof goes the same for either one of them. Anyway, so it follows that there is a ball surrounding z naught for which these are also positive. But now, if we take gamma to be the boundary of the ball, then clearly the integral around d gamma of uy plus vx dA is non-zero, and that the closed integral around d gamma of ux minus vy dA is also non-zero. In fact, it's positive. But we assumed that the closed integral around gamma of f dz is 0 for any curve. That's the end. Okay. Let's see where we are. for it?
No.
This takes us to the next theorem very nicely.
So let's.
Theorem. This is called the Cauchy-Gauer-Sacks theorem. Cauchy-Gauer-Sacks theorem. Okay. Let F be analytic. In some region D in C, then and let consider gamma be a function from R into D gamma subset of D. And let that be a closed curve, in D. Then the integral along gamma of f dz is 0. Again, so the proof for this is actually very straightforward. So proof. Well, we know that f dz we already solved is equal to these two integrals, right? So the integral along gamma of f dz equals the double integral around d gamma of u sub y plus v sub x dA plus d gamma u x minus v y dA from here. But since f is assumed to be analytic, we have that u sub x equals v sub y, and u sub y equals minus v sub x. Okay? But then, the integral of f dz equals the double integral d gamma of uy vx, but uy is minus vx, 0 dA, plus the double integral around d gamma of ux minus vy, but ux is vy, and so again that's 0 dA, and this equals 0, and that's the end. Okay.
All right.
Now we make an extension. We're going to prove another theorem that follows from these. So the new theorem does it have a name? Does not. It's more of a lemma. If f is analytic, well, let's do it differently. Define. So let gamma 1, be a closed curve, and gamma 2 a closed curve, inside gamma 1. In other words, so i.e. d gamma 2 is a complete subset of d gamma 1. Right? Now, let f be analytic in the region, right, D gamma 1 intersection D gamma 2 complement. In other words, so the picture, this is gamma 1, and this is gamma 2, and this region is D gamma 1 intersection D gamma 2 complement. Then, says the theorem, the integral of the closed integral of f dz around gamma 1 is equal to the closed integral around gamma 2 of f dz. That's the theorem. Let's make a note. If f analytic on d gamma, or d gamma 1, then 0 equals the integral around gamma 1 of f dz, which of course will equal the integral of gamma 2 f dz, which as well will be 0. So the condition is trivially satisfied through this theorem over here. So this is my Cauchy Gauer-Sat theorem. Bracket. All right. Very nice.
Is there a tissue to be had?
No, I don't see one. All right. So the question now is, well, what happens if f is not analytic in this region? So this region over here is d gamma 2. And what happens if f is not analytic? So we can't use the Cauchy theorem. Well, what we could do is we can create a closed line integral, which does only surround analytic regions on its interior, and which will approximate the integral of the sum of these two curves. So let's have a look at what that's all about.
So let's see. Well, we could go to that board. Right. All right. Here we are.
So okay, so what do we want to show? All right, so now consider the following curves. So first, delta 1. What is delta 1? Well, let's make an image of it, then we'll define it. So again, this over here is gamma 1. This over here is gamma 2. Let's say that gamma 1 at time t naught, so in the beginning of time, is here. So this is gamma 1 of 0, and it goes in this direction. So define delta 1 to be the shortest path connecting gamma 1 of 0 to gamma 2 of 0. And let's say, without loss of generality, gamma 2 of 0 is right there. Okay, so 4. So what is it? It's equal to gamma 1 of t when t equals 0. It's equal to gamma 2 of t when t equals 1. And let me make this larger. And it's equal to lambda, well, let's just say the shortest path between gamma 1 of 0, gamma 2 of 0 for t greater than 0, less than 1. All right, that's our first new curve, that's delta 1. We can now define delta 2 to be, in a sense, the opposite. So, gamma 2 goes around this way. What we are going to consider now is delta 2, which starts at gamma 2 of epsilon and goes to gamma 1 of epsilon. Right? It starts at gamma 2 of epsilon and goes to gamma 1 of epsilon. So it's gamma 2 of epsilon for t equals 0, and gamma 1 of epsilon for t equals 1, and shortest path from gamma 1 of epsilon to gamma 2 of epsilon. So again, this is the shortest path. Okay. With these curves defined, now we will define the third curve. This third curve will be lambda. So what is lambda? This should probably be way bigger. I'll put it in later. So lambda will be delta 1 for t between 0 and 1. Okay? I'll just put it in later. Alright, so delta 1 of t between 0 and 1. It will be minus gamma 2 of t, I will say, of t minus 1 for t greater than 1, less than 2, right? So we go in this direction, and then we go in this direction, go around, all the way until, well, t doesn't actually go up until 2, but it goes up against the 2 minus epsilon. So that at maximum t we get t minus at maximum t we get 2 minus epsilon minus 1. That's 1 minus epsilon. But of course, gamma 2 of 1 is the same as gamma 2 of 0. So gamma 2 of 1 minus epsilon is the same as saying gamma 2 of epsilon if we're going in the reverse direction. Okay? And then what it is this over here. It's this delta 2, t minus 2, and this over here is t greater than or equal to 2 minus epsilon, less than or equal to 3 minus epsilon. All right, so it's now, so over here, 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 and now we're going to go from gamma 1 in the positive direction of t minus 3. So at maximum t, at minimum t, we get 3 minus epsilon, so that's 3 minus 3. It's 3 minus epsilon minus 3. The 3 go away, we get a minus epsilon. So then really it should not be t minus 3, it should be t minus 3 plus 2 epsilon, and t over here is greater than 3 minus epsilon, less than or equal to, we want it to go all the way up until from here all the way to this point, gamma gamma 1 of 0. And so that means that we want this inside to be 0, which means that we want t to be 3 minus 2 epsilon. 4 minus 2 epsilon. 4 minus 2 epsilon. Again, when t is equal to 4 minus 2 epsilon, we get 4 minus 3 is 1, minus 2 epsilon plus 2 epsilon is 0. We just get gamma of 1, which is gamma of 0, and that's what we get. Alright, so now, that's what we have. Consider then the integral along lambda. The integral along lambda is this, back down, and all around of f dz. This is the integral along delta 1 of f dz plus, or really minus, the integral of gamma 2, but over here it's not gamma 2, it's only gamma 2 from really 1 to, well, really from 0 to, from 0 to minus epsilon. It goes from 0, well, if we went this way and we stopped it over here, we would go from, so t is greater than 0, less than 1 minus epsilon. Okay? F dz plus the integral. Now we go along delta 2, and it's a complete delta 2 of f dz plus the integral, plus the integral gamma 1. But we're starting at gamma 1 of epsilon, and so t greater than epsilon less than 1. Say greater than or equal to, all of these can be equal to as well. It's not a problem. Of f dz. Okay, that's one line integral that I wish to consider. Notice that this is a closed line integral, right? Because we go in over here, around here, here, and here. We end at the same place. And so this over here must be 0. It's closed. Now, consider further the integral along delta 1 through gamma 2, then back along delta 2, and then in the opposite direction along gamma 1. So further, let's call this integral lambda 2 of f dz, and we define it to be the integral to go along delta 1 of f dz. Of course, this is a closed integral because it makes a closed circuit. Now, you go plus the integral along gamma 2, but only from t greater than or equal to 0, less than or equal to epsilon of f dz, plus the integral along delta 2 of f dz minus the integral along gamma 3, but right, we're going the opposite direction, and over here t greater than or equal to 0, less than or equal to epsilon of f dz. And this as well equals 0. Now, since both of them equal 0, we can add them. But, in particular, we can subtract them. So if we subtract them, the delta 1s disappear, and the delta 2s disappear. And what we get is this over here.
let's see what this gives us.
So, the closed integral along lambda 1 of f dz minus the closed integral around lambda 2 of f dz. By the way, this should of course equal 0. It hasn't changed. The deltas, this delta and this delta cancel, this delta and this delta cancel, and what we get is this one. So this is minus the integral from under gamma 2 from where t goes from 0 to 1 minus epsilon. So this is gamma 2 t greater than or equal to 0 less than or equal to 1 minus epsilon of f dz. Now, of course, it's this minus this. So minus the integral along gamma 2 when t is greater than 0 less than epsilon, t greater than 0 less than epsilon, plus, f dz, plus the integral along gamma 1, that's over here, of f dz, where t goes between epsilon and 1. So t greater than or equal to epsilon less than or equal to 1 of f dz minus, but minus minus is a plus, plus the integral along gamma 1, t greater than or equal to less than or equal to 0 and epsilon. 0 epsilon f dz. What do we have? Right? What is this? Well, over here, if t goes from 0 to 1 minus epsilon, is this a minus or a plus? Let me see. This is a minus minus. Okay. So so what we have here, this is t going from 0 to epsilon. So that's this, and this part over here, well, really it's minus. It's minus this because we subtracted it. So we're really going the other direction. It's clear that if I take this line integral and I add to it this line integral, that I get just the total. So this is the integral closed around gamma 2 of f dz. Again, this is 0 to 1 minus epsilon, and this takes that 0 to positive epsilon, but it's in the negative direction, so it's epsilon to 0. And this is as well minus, so really it's this is 0 to epsilon, but in the opposite way, and this fills in the gap, and so what we get is the complete gamma 2. Similarly over here, t goes from epsilon to 1 in the first part, and in the second part it goes from 0 to epsilon. Well, really, it goes from 0 to epsilon, then epsilon to 1. That's the complete gamma 1. So this is, of course, minus plus the integral around gamma 1 of f dz, and this equals 0. So finally, we get that the integral along gamma 1 of f dz is equal to the integral along gamma 2 of f dz. That's the end of the proof. Okay. Let's see what's next. All right, the Cauchy integral formula. Theorem. All right, the Cauchy integral formula. The Cauchy integral formula says, so let f be analytic in a domain D, subset of C, then f of z naught equals the closed integral around some curve gamma of f of z, but of course this would be 0. We must divide by z minus z naught dz. This is the theorem. It's a very grand, very grandiose theorem. I really need a tissue. What happened to my tissue? Alright, I'm going to pause this video so that I can get a tissue.